I'm Casey, so I'm a researcher at OCaml Labs within the University of Cambridge. I'm going to talk about this particular library that we're building in the context of Multicore OCaml called Reagents that allows you to basically express lock-free programs in a nice fashion. We'll see what I mean. All right, it works. So before I actually talk about reagents, it's perhaps useful to place reagents in the context of the wider Multicore OCaml work. Multicore OCaml is a project that's being led from OCaml Labs, which tries to add native support for concurrency and parallelism to OCaml, addressing the long awaited feature that everyone complains about. But really, one thing that we've made very clear in the design of Multicore OCaml is we have this deep distinction between concurrency and parallelism all throughout the stack. In particular, concurrency is a program structuring mechanism. Concurrency is what you do when you need to overlap your I/O computation with your actual program that runs like computations. And parallelism is what you need when you want to make your programs go fast on multiple cores. So in keeping with this, Multicore OCaml provides two different APIs for dealing with concurrency and parallelism. The unit of concurrency in Multicore OCaml is what we call fibers, which are language level lightweight threads. And fibers are really, really cheap to create. You can create, as a data point, you can, on my laptop, I could create up to 12 million fibers per second on one core and up to 30 million fibers per second on 4 cores. The numbers really don't mean anything except that as a programmer, if you want to use concurrency using fibers, you shouldn't have to think twice. On the other hand, we also have domains, which are the unit of parallelism, and domains directly map to system threads. So you have a limited number of domains that you can create, and it's typically the number of cores that you have. So you typically start your program with n domains where n is the number of cores that you want to provide your application. On top of this, Multicore OCaml exposes what is called as algebraic effects and handlers, but also provides a very small domain API for creating domains. Algebraic effects are this very academic concept that we've brought into OCaml. In short, what they provide is a way to program with control effects, such as control, inversion of control, non-determinism, concurrency, and so on. And the primary reason for introducing effects into OCaml is to allow the programmer to write schedulers for these fibers to map them on top of domains as libraries for OCaml. So essentially, the programmer can write their own libraries, and the idea is that the programmer really knows what they're doing in terms of their application. So if they can write their own schedulers, then the programs can actually be better designed. So we have, we imagine cooperative threading libraries to be written using effects, but any half-decent parallel programming language also needs to provide a very good library for shared memory parallel programming, and this is where reagents come in. So developing industrial strength concurrency libraries is an arduous task. And libraries like java.util.concurrent for JVM and concurrent collections for .NET represent years worth of expert programmer effort, and they typically provide a very large number of synchronization and data structures. So they do provide very specialized data structures. For example, java.util.concurrent provides multiple different concurrent queues that are distinguished based on their blocking behaviors, their internal representation, whether they are synchronous or not, whether the thread provides priority, and so on. This might look like an exhaustive list, but there's a fatal flaw in that these libraries are not composable. So as a programmer, if I have, say, a particular operation which pushes an element in the queue, and I want to build an abstraction, a function, which pushes 2 elements into the queue atomically, I won't be able to do it unless the library itself provides such an operation, right? But it's also the case that if you really wanted to extend the library with such an operation, you have to really think about it, because these libraries are written with subtle invariants about their safety and performance. You don't want to screw up because you want to add a new feature into it. So these libraries evolve very, very slowly. So clearly, we don't want to be in this boat for Multicore OCaml, because we want the library to actually move fast, integrate new features, but also provide the capability for the programmers to extend the libraries as they wish. So the big question that we wanted to answer is, how do you actually build lock-free programs that are composable? So the programmers can compose individual operations into bigger atomic blocks, but also extend these libraries, provide other operations which can be further extended, and so on. So at this point, it's quite useful to clearly distinguish what we mean by lock-free programs. So lock freedom is this guarantee which ensures that if you have multiple threads that contend for a shared resource, at least one of the threads makes progress. In order to understand this, you can contrast it with this weaker property called obstruction freedom, which provides no such guarantee, but only ensures that a single thread in isolation makes progress. So essentially, if you have obstruction-free programs, they can live lock, but lock-free programs won't. You also have this other guarantee called wait freedom, which is much more stronger, which says that under contention, if you have multiple threads, each of them makes progress. So, but it's typically the case that wait-free programs, data structures are really difficult to write, and there are very few that are out there which are proved to be wait-free. And lock-free programs generally capture a large number of useful patterns, and in this work, we are going to concentrate on lock-free. So, quick question, how many of you have actually programmed with compare and swap instructions? All right, great. So, compare and swap is this the primary tool for lock-free programmers when they write parallel programs. And there are many different variants of compare and swap, and essentially all of them boil down to this particular pattern, where compare and swap is applied over a shared memory reference. It takes in an expected value of the reference and also takes in a value that needs to be written into the reference. And what it does is atomically check whether the reference has the expected value, and if so, update the reference to the given value. And if not, cache is supposed to fail. Like shared memory multi-core processors provide this particular compare and swap instruction or other variants natively, but one thing that connects all of these instructions is that they're really, really expensive. They're expensive not because the instructions are expensive. They're expensive because they involve a full memory barrier, which flushes the store buffer. So you have to be really careful, even in the presence of compare and swap, to be very stingy about when you use them. So in order to make some of the ideas that come up in the sequel more concrete, let's imagine that you're building a lock-free stack data structure, and head currently points to the node 3. And suppose the thread wants to add, say, an element 7 into the push an element 7 into the stack. What it tries to do is to attempt a cache, trying to update the head to this new node. But in the meantime, you could have other threads that update the head to this element 5. So this causes the cache to fail, and then the whole protocol has to be retried, and the only guarantee that you get is eventually the whole protocol will succeed and the element will be enqueued. So you can sort of write this program in Multicore OCaml, imagining a cache that is exposed to the programmer. The key takeaway from this slide is that we represent stacks as a list reference, and push simply dereferences the stack, tries to cache update the stack to the result value, and if it succeeds, then we are done. If it fails, we back off and retry the whole protocol. the back off here is really important, right? So you don't want to keep banging on the cas because that leads to performance degradation overall, and you're not going to do any better than just locking the whole stack and doing this operation. So just to complete the whole thing, so try pop is really similar, where you try to dereference the stack. If it's empty, you return none. If it has elements, you try to cas update the stack to the tail of the list. You back off and retry if you fail. Like, all of this is fine until I want to do something like this, where my aim is to atomically pop an element from stack S1 and push it into S2. Like, it's easy to see that even though each individual operation is atomic, the whole protocol is not, because we don't have any tools in our arsenal to put them together. And if you did want such an operation, the library has to provide such an operation, like the library writer has to provide such an operation. This is a problem, right? So this is not what we want to do. And to summarize the whole problem, while concurrency libraries are indispensable, like they have to be written by experts, they have to take care of all these subtle retry and all of these properties, they are very hard to build and extend. So Reagents is this very nice library that provides scalable concurrent algorithms that can be freely extended and built by the user of the library. For example, under Reagents, we have this sequential composition operator, this triple arrow thing, which allows you to compose two individual operations, like compose them atomically so that the whole transfer from popping from S1 and pushing into S2 is atomic. So Reagents were introduced by Aaron Turon in this in his PLDI 2012 work. It's a really good paper. So if you're interested in reading a nice paper on PL design, I would recommend reading this paper. One of the nice things that the paper says is it provides this ability to combine sequential put things sequentially similar to software transaction memory, but also combine things in parallel similar to join calculus, but also perform selective communication similar to join calculus, and I think Go channels also provide this select operation. The nice thing is you can combine all of this in a single library, but still be lock free. That's the key, right? So your algorithms won't live lock if you build your algorithms with Reagents. And the key part of how all this works is composition. So since we are functional programmers, we like function composition. So if you have a function that goes from A to B and a function G that goes from B to C, you can compose them together to get a function that goes from A to C. When functions represent lambda abstraction, reagent values are also similar computations that take an input of type code A and return a type value of type code B. We write the types as follows with this OCaml notation, which is code A, code B, reagent.t. And similar to applying functions, reagent give you a way to run the reagents. While supplying an input value, it runs the whole reagent protocol atomically and then returns you a value. Now the thing is, you also want your threads to somehow interact with each other. And when you talk about thread interaction and communication, like you have these two opposing camps, one which argues that all threads must interact over shared memory, and the other which argues that all thread interactions must be over communication channels, just like actors, where they have no shared memory, but then keep exchanging messages over type channels. Reagents nicely incorporate both of the models together, so you can program with either in this common framework. So a channel is really an endpoint which accepts a value of type code A, and you can receive messages of type code B in it. And creating a channel gives you a pair of dual endpoints which have dual types. You can see that the types are reversed. And the only operation that you can do on a channel is request to swap on the channel. When you do a swap on the channel, if you don't have a matching swap on the dual channel, your thread blocks, waiting for a match. And then when you do have a matching swap, the value of type code A is exchanged to the matching channel, and the value of type code B is received from the matching channel. So basically, what reagents provide you is this synchronous swap channel abstraction, but you can use reagent combinators to build all sorts of abstractions like non-blocking channels, like point-to-point channels that are asynchronous, and so on. So this, while this channel endpoint represents message passing, as I mentioned before, reagents also provide you shared memory. The type of the shared memory reference is alpha ref, as one would expect, but you don't have the usual reference update function. Instead, you have this weird-looking function called UPD, and what it does is it takes in a shared memory reference, but it also takes in the function f, which is applied to the current value of the reference, an input value of type code B, and f is supposed to return an optional value. And if f returns none, the whole thread blocks until you have some other write on this particular reference. At that point, the thread is woken up and the whole protocol is repeated. And the whole operation returns you a reagent type. Like, all of this might look weirdly complicated, but what it generalizes is it generalizes to transactional variables associated with read logs. So we'll see how we'll use this. But the real power of reagents is combining two reagents together. Suppose I have two reagents R and S, each of which goes from alpha to beta. Then I can combine them using the choice combinator to produce a new reagent whose semantics is that it will first try the reagent R. If that reagent blocks, then it tries to run the reagent S. And if both of them block, then the whole reagent blocks. Otherwise, it just gives you the value that is enabled by one of the reagents. So this is similar to the selective communication operator that you have in concurrent ML and so on. And this represents disjunction of reagents. You could also combine reagents in parallel, where if I have two reagents R and S that go from alpha to beta and alpha to gamma, essentially, you can combine them in parallel such that the composite reagent will only fire if both of the reagents are enabled. And all of this happens atomically. And reagents take care of the underlying protocol, so none of this deadlocks. So it's quite nice. So you have these four operators, and you can do fancy things with this. Now here's an implementation of the lock-free stack, but built with reagents. So again, we use a list reference to represent the stack. And then the push operation, what it does is it uses the UPD combinator to update the stack to the new value. And the pop-up operator is more interesting. It tries to dereference the stack, and if the stack is empty, returns none. And due to the semantics of UPD, it automatically blocks. And it's woken up when there is a corresponding push or a pop on this particular reagent. So the key takeaway from this slide is that so the implementation itself is no more complicated than a sequential stack implementation. But the reagents take care of all the nice, like all the difficulties such as retry loops and dealing with thread parking and wake up and so on under the hood. But the third but main point is that all of these operations are still lock-free, right? So you don't give up the lock freedom when you build data structures using reagents. Now you can do fun things with the reagents. So to be sure, if you look at the type of push and pop, they return a value of type reagents so that you can compose them together further. Now I can transfer elements atomically from one stack to the other by just sequentially composing operations. I can consume elements atomically from two stacks by just composing them together with parallel composition. I can also wait for inputs from any one of the stacks by using the choice combinator. But I can also build higher level abstractions that are built out of individual reagent combinators. Suppose I want to transform like arbitrary blocking code into a non-blocking version. Like this looks like a really difficult problem because the notion of blocking and non-blocking is deeply embedded within the logic of the function. And the way you do that in reagent is using two other combinators. One is lift, which lifts a pure function to a reagent, and another is a constant, which always returns a constant value. And you can sort of put them together into an attempt reagent, which takes any reagent, blocking or non-blocking, and always transforms it into a non-blocking reagent. The way we do that is we compose the original reagent R suffixed with suitable value coercion and put it in a selective communication with constant none. Because our selective communication operator is left bias, it is always going to try the first option, which is the original reagent R. If it blocks, it will return constant none. Hence, the whole protocol is non-blocking. So using this, you can play cool games where I can take the blocking pop implementation and build a try-pop implementation by just attempting the pop. So it gives you this very nice abstraction where you can sort of play around with these notions of blocking and retry in a declarative fashion. So you can also do fun things where you can provide an elegant solution to the dining philosopher's problem. So the main problem is that, so the problem as it is described is that you have a bunch of philosophers sitting around a table and they share their forks with the neighboring philosopher. So each philosopher takes a turn between thinking and eating, and they can only eat if they have both of the forks. And you find this problem in all of the concurrency 101 textbooks as an example for deadlocks and live locks and so on. So the important thing is to ensure that no philosopher starves, because you can always, it is so easy to just say, okay, few of the philosophers are nominated to be eating, others are starving, and you have no problem. So this in general is really difficult, but you can build a very elegant solution with reagents. So we model forks with endpoints. We have two options, operations, drop and take, each of which is an endpoint. And we make a fork by making a pair of channels which are duals of each other. And drop and fork are just defined as swapping on the corresponding channels. Now, here's the cool part, right? So eat is just the code that's displayed there. I think the most important line is the first one, which says do a parallel composition between taking the left fork and the right fork. So the semantics of parallel composition says that it will only be enabled if both of the operations can be atomically done, right? So this particular operation is sufficient to ensure that a philosopher will eat only after he grabs both of the forks, right? And the notion of deadlocks and retry and all of that is hidden underneath behind the reagent implementation. And in order to drop the fork, we just spawn new threads so that we can drop them asynchronously. And if the underlying thread is, underlying scheduler is fair, you have the assurance that all of the philosophers will eventually get to eat. And few points about the implementation. So the way reagents actually work underneath is you have this two-phase thing. When you run a reagent, you have a CAS collection phase where you try to accumulate all of the CASes, and then there is a second phase where you try to attempt all of the CASes using a KCAS mechanism. Like modern architectures don't provide a KCAS, so we implement it in software, but that's fine. When you have a failure in accumulating the CASes, what you have is a permanent failure, which is I cannot run this protocol anymore, so the thread blocks or tries a different alternative. But when you have a failure in the second phase, it just means that you have an active interference from other threads that are concurrently executing in the system. So you just retry the whole protocol again. So the important thing to take away from this is because you have this two-phase separation, you can sort of think about implementing reagents using hardware transaction memory. So Intel's TSX extensions provide this limited form of transaction memory where instead of doing KCAS in software, you can sort of like let the hardware do it. So reagents are ready for like taking advantage of HTMs. So we've implemented reagents. We also have a bunch of data structures that we build, data and synchronization structures that we build. It's important to say that these data structures are like really small, maybe tens of lines of code, but they have all the nice properties that you would expect from a log-free library, in that they do all, like the entire library is log-free, they are composable, they can be freely extended, you can actually read the code, which you can't do with most log-free libraries that I've seen. So the library is available in the OCaml Labs repository. So if you do find this interesting, go play with it. Do build like other data structures. See what you think. Yeah, that's all I wanted to say.